my big pleasure to welcome our speaker today. Is Professor Ya-xiang Yuan from the Chinese Academy of Sciences. So this is the last talk of the second season of OWOS. There will be a third season, which will start in January, on January 18. So Professor Yuan received his PhD from the University of Cambridge and moved to the Academy of Sciences, where he was in charge with the leading of many important research institutes and key laboratories. He is one of the most famous Chinese optimizer with many students, with very important publications. He won many awards. But before coming to his talk, I like to mention one thing which I liked very much. So this is something which I found on his website. Professor Yuan is writing, "I was a farmer and remain a farmer forever in heart." So, Professor Yuan, the floor is yours.
Thank you much. Thanks, Chair. Thanks very much for the nice introduction, and also thank you much for the invitation for me to have the opportunity to give a talk in the One World Optimization Seminar Series, the last one of these in this year. So the talk today I'm going to talk is about orthogonalization-free approaches for optimization problem on Stiefel Manifold. This is a joint work with Dr. Bing Gao, who is my former PhD student now doing postdoc in Leuven in Belgium, and also my colleague, Dr. Xin Liu, Professor Xin Liu, in the Chinese Academy of Science, and also my current student, PhD student, Na Chan Xiao. So first of all, I want to see the problem I'm going to talk about is a very simple one, which is the minimized function of matrix, which subject to the constraint where the column of the matrices are orthogonal each other with orthonormal column. So that means if you have a matrix of n row and p column, then the constraint, the number of constraint will be p times p plus 1 divided by 2 constraint. Even though this is a quadratic constraint, but it is a non-convex because it's think about p equal to 1, which is the surface of the ball. For this set, the constraint, it also have a name called Stiefel Manifold. So this is a very simple, looks like very simple problem. But why we're interested in this problem? First of all, this very special manifold optimization. Currently, I'm working a group and people working on manifold problem, and optimization is one of them. And also, even though the form of this problem is very simple, but there are a lot of applications can be formulated in this simple problem. For example, I give a few examples. For example, you have a quadratic object function where you minimize the trace of matrix X transform AX subject to the orthogonal constraint. That is basically you're trying to find the eigenspace of the leading eigenvalue corresponding to the eigenvalue spaces. There is a lot of work have been done on this problem. For example, LOP-PCG and also SVD and RBIT. Also, that is subspace approach, and also the part function approach also have a lot of work in this direction. For smooth object examples, the discretized quotient total energy minimization is also a special Stiefel manifold optimization where you minimize the energy function subject to the orthogonal constraint, where the energy function, which consists of 5 terms, so each term they have different physical meaning, different energy of the structure of electrons. There are famous algorithms like the self-consistent field iteration, and also you can also doing by solving this minimization problem by solving the nonlinear eigenvalue problem. So SCF iteration basically is to solving the nonlinear eigenvalue problem by solving linear eigenvalue per iteration. So that means you solve a linear eigenvalue problem, you get the density, and you put into the eigenvalue problem, and then you're solving the linear problem once again by keep iteration. That is a very simple approach. And also you come by optimization approach. There's also different approach for this. Another thing is about the clustering, where if you have a lot of data want to classify, and they have different formulation. One way is by using the graph or technique, then you can end up a combinatorial problem, and you're using relaxation, then you get a constraint optimization problem, which will be end up orthogonal constraint. So for example, the ratio cut by Chen Liu, and also they have the connect subgraph by Liu and his collaborations, and we end up the formulation also orthogonality constraint. They also have non-smooth objective functions to minimize with the orthogonal constraint, particularly for lot of data analysis problem. For example, the sparse principal component analysis problem, where you minimize the trace function plus one norm of the matrices subject to the orthogonal constraint. And also the similarly non-smooth term, really basically depends on what kind of sparsity you require about your statistical modeling. For example, you have the 2-1 norm and also the W transfer Y1 norm, this kind of non-smooth term. So now I will be willing to go quickly to the smooth object case. First of all, there are already many existing methods for solving the orthogonal constraint problem. One way is doing optimization directly on manifold, matrix manifold. And basically, many of the standard nonlinear optimization technique can be extended to manifolds. For example, steep descent, conjugate gradient, Newton, cosine Newton, or trust region, and Gaussian search in canonical matrices or the Cayley transformations. All these you can do optimization technique direct on the manifold. And also because most of the manifold you can think about like a constraint, you can look at the tangent space of the manifold. That means you basically can do in search in the tangent space as well. That is the second large group of methods. And also they have other types of works. I will not go to mention in detail. So why we are, already there's a lot of work, why we want to do or our approach to considering this whether looks very simple problem. First of all, the bottleneck for orthogonality constraint problem is particularly when P is very large, you have a lot of column. So many of the methods, you keep doing orthogonalization, which is not easy for parallel computing. Even the column-wise parallelization is also not good, suitable for scalability. So our approach today, I'm going to talk is mainly based on infeasible method. So that means why we're thinking about infeasibility approach is we don't want to keep our iteration on the manifold, we notice by doing this can be very efficient, even not in the parallel computing, even though in the end we're trying to, for doing really serious large calculation, we use parallel computing. So the way we're trying to doing this is by the penalty function approach, which is a very simple, classical idea for constraint optimization. Even though, I mean, for non-smooth penalty function, this is not doing good, not easy for use a penalty approach, particularly for Lagrangian, augmented Lagrangian penalty function, because the non-smooth penalty function, you don't have the Lagrangian multiply in closed form. So we're thinking about not general non-smooth penalty function. We're thinking about a particularly very easy or simple non-smooth function. So now I'm going to mention starting from the very simple case. So think about the augmented Lagrangian function method, which is now widely used for data analysis problem. So for example, ADMM, which is basically, alternating technique using the augmented Lagrangian penalty function. So augmented Lagrangian function can be traced back to Mike Power and also Hastings in the late 60s last century. So basically you have Lagrangian function and plus augmented term. This is the function is exact penalty function if you have the correct Lagrangian multiplier. So basically the Lagrangian Lagrangian augmented Lagrangian penalty function approach is you choosing a Lagrangian multiplier, you update the prime variable by minimize the augmented Lagrangian function. So you get solution, you update the multiplier by dual extent of the function. So basically you fix the Lagrangian multiplier, you get the variable, then you update the multiplier. That is by repeatedly doing this way. This is a very efficient approach, but however, we found for our particular problem with the orthogonal constraint, this way of doing this is not an efficient way. So because it does not using the structure of the particular problem. So why? Because this our problem is too simple. I mean, to use the general augmented Lagrangian approach. For example, for the orthogonality constraint, then we can easily get the first order optimality condition. So noticing the first order optimality condition, we can easily obtain the closed form for the Lagrangian multiplier, which is X transpose of the grad of the function. So any first order stationary point must satisfy this closed form solution. Another observation is we know because the constraint X transpose X equal to I is symmetrical. That means the Lagrangian multiplier also has to be a symmetrical matrix. That means gamma have to be symmetric, but have the closed form of X transpose grad of the function. Of course, X transpose the grad of F need not to be symmetric. So that means we symmetrize this gamma. So that means we can update the multiplier in a closed form by choosing gamma is the mean value of X transpose the grad of F, and it is symmetric matrices. So that means is by this centralizer of X transpose the grad of F, we get a closed form solution for the Lagrangian multiplier. In doing this way, instead of update the Lagrangian multiplier, we use a closed form solution. This is a very simple idea, but it works very good. That's why we have suggest a proximal linearized augmented Lagrange method, which we call the PLAL, which is basically you using this closed form Lagrange multiplier, you get the augmented Lagrange function. We use a fourth order method, then we can get the update. We prove this method at global convergence and have a local linear convergence rate. And numerical results showing our approach is compatible with most of the existing algorithms. So that is very encouraging, even though it's a very simple idea. Later on, we extended our algorithm or modified our algorithm by giving a version which is called a column-wise block minimization of the PLAM, which we call the PCAL. In this way, we're using the graph of the augmented Lagrange function, each column, and updating each column of the matrix by the column of the gradient. So that means we update the column-wise, and we normalize the vector of each column. So that is a very easy way to scale the vector. And we notice, even though we're doing this, we didn't realize this will be improving the original algorithm. But in the end, it actually, this new method is much better than the originally PLAM. First of all, it's not sensible with the beta, the party function. And also, the numerical performance, the PCAL, is much better than the PLAM. And moreover, of course, it's much better, has much better scalability. So it's good for parallel computing. We have done some numerical results and showing even for some calculation of electronic structure with n equal to 380,000 row and also 1,000 column of the matrices. And you can see the speed up of the method is quite good. So even though we get a better result from the PCAL, better than the PLAM, but we still not, theoretically, we didn't understand why the new method is better than the old method. And also, we have to have a good understanding of the math function. We're using the closed form of the Lagrange multiplier. And also, we want to study a possible extension with the second order method. So first of all, now look at the party function. First of all, we prove if X star is the first order stationary point of the original optimization, the orthogonal constraint problem, then of course it will be a first order stationary point of the party function. But far about the other way around. That means if we now get a first order stationary point of the party function, whether we can show in it's originally a first order stationary point of the original problem. This is only true if it's a feasible point. If it's not feasible, of course, it won't be a first order stationary point, because if you have a stationary point which is infeasible, if you know, so that means we have to show in if we get a stationary point, then have to be a feasible point. Another difficulty we notice is we're using the closed form Lagrange multiplier. We put in, get this party function. Unfortunately, this function is unbounded below sometime. Actually, we give a very simple example. The function is very simple, which is 1/4 of x transpose x, the f norm square. And we notice for this very simple function, we put the Lagrange multiplier or closed form put into the augmented Lagrange function, and no matter which beta you choose, this function is unbounded below in the whole space. So that means originally we thought we have a very nice bounded function because we use a closed form. Lagrange multiplier is the ideal formula for the Lagrange multiplier, should be have a nice bounded function. But unfortunately, this is the blow. And because this function is unbounded, because normally we try to minimize a bounded function to get the stationary point. So what we could do? So because this function is unbounded in the whole space, so why don't we, because we know the Stiefel manifold is the bounded set. So why don't we restrict this bounded function in a bounded set? If this bounded set contains the Stiefel manifold, then it is enough. So that means we're thinking about minimize the bounded function within the matrix between a set of M, capital M, as long as this M which contain the Stiefel manifold, then that is okay. And we keep our iteration of the minimizing the bounded function. If it go out to the feasible, then we project it back to M. Of course, to construct this M, it has to be very easy to project back to M. So there is a very trivial way to choose this capital M. For example, we can choose a ball. As long as the radius of this ball is greater than the square root of P, then we can prove the Stiefel manifold will be inside this ball. And also we can use the convex hull of the Stiefel manifold. And also we can using a convex hull of the oblique manifold. The oblique manifold is each column, the two norm of each column is less than 1. So they have different way of choosing this. So while we're going to prove or approach to minimize the bounded function within the bounded ball is working, we need to have some assumption. The assumptions are really well standard. First of all, assume the object function is differentiable and the gradient of the function is Lipschitz continuous. And also assuming it's twice continuous, differentiable, and also the second order derivative is Lipschitz continuous. So we have two assumptions. Even though these both assumptions does not imply the existence of the gradient or the second order gradients or the Hessian of the originally Hessian the bounded function. Our first result looks very interesting as we prove if the bounded parameter is large enough, then the first order stationary point or the bounded function will be either a first order stationary point of the original problem, or the point will be far away from the Stiefel manifold. This is a very interesting result. That means we're showing by solving the bounded function, get the first order stationary point of the bounded function. Either you get the first order stationary point of the original problem, or you'll be far away from the Stiefel manifold, because the minimum eigenvalue, the minimum singular value of these matrices of the solution of the station point will be very small. Think about the beta is very large, because we know the Stiefel manifold or the singular value will be equal to 1. So that is a very nice result. So that means by solving the bounded function, we can either get solving the first order stationary point of the original, or you'll be far away from the Stiefel manifold. So if we get a solution on the Stiefel or near the Stiefel manifold, then we get the solution on the manifold. So that is interesting. Another thing we we have to we show the next step is we showing if you prove a result, we prove a result, all the points near the Stiefel manifold are better than the point which is far away from the Stiefel manifold. Of course, we're thinking about in the bounded set because we have X belong to the capital M constraint. So that means if you have a method to try to find in this capital M, to find the global minimizer of this problem, it have to go close to the Stiefel manifold, not far away. Because far away, because the info of the far away point will be worse than the worst point near the manifold. So that is, if we're trying to get a global minimize of the Poynter function, then it has to be on near the Stiefel manifold. Another thing is about the second order stational point. Then we can also show you some results. Similarly, if beta is sufficiently large, then we can show you any second order stational point of X. Then if on the manifold, it also a second order stational point of the original problem. So that is the theoretical result. Having this theoretical guarantee, that means we're safe to solving the Poynter function in the ball. So originally we have a constraint problem. Now we have a simple constraint problem. We're solving the ball, which is a convex constraint. So that means basically originally we want to solving a non-convex problem, which is Stiefel manifold. Now we convert into at least we have the convex ball to solving in the ball the global minimizer of the HX. As long as this ball is large enough, actually we know as long as the ball, the radius of the ball is greater than the square root of P. So this is now is a very simple problem. You have a ball, you minimize H. So H is now, as I said, is smooth function. So now we're doing this, we use the gradient of this, the Poynter function. As I said, the Poynter function is depends on the closed form of the Lagrangian multiplier, but the Lagrangian multiplier itself is depends on the gradient of F. So that means even we compute the gradient of the Poynter function, which will have the term of depending of the second derivative of the original function. That is not something we don't want to compute, because in calculation we don't want to compute second order the H of the objective function. But fortunately, I mean this term, the term which depends on the second order term is very small. If you are close to the manifold, then we can ignore. That is the line we light on the red term. So that means we just take a part of the gradient of the Poynter function we denoted by Gx. So this is the kind of approximation of the gradient of the Poynter function. We use these to do our calculation. So in that way, we use the approximation of the gradient of the Poynter function to do in a first order step. Then we get our very simple first order method based on for the convex constraint problem. Even though I mean the H is not convex, but we use first order method. We don't care about whether you're convex or not convex. So locally, we always approximate the function by the linearized function. Then we're using first order step. Then, but it is convex constraint. Then we can quite do a gradient method. If you go out the ball, we just project back to the ball. Very easy. So it's a very simple algorithm. We call the PenCF, and it works. And we can, first of all, we can prove the theoretical results of the method. We we can show you the convergence, the global convergence of method. That means because it's in a bounded set, and we can show you at least one of the cluster points will be a stationary point. And we can also give in some theoretical results about the conversion rate of our approach. Each is a first order method, we can only prove Q linear conversion rate. So that means if the point which is close, starting point is close to a stationary point, then we're showing the method will be convergent Q linearly when it goes to the local isolated local minimizer point. Then this, we have done this. So from this constraint, the PanCF give our backward, now remind us why our method PCAL, which remind you we use column-wise method, is better than the original PLAM. So basically the PLAM, our original method, is you can think about it, we don't have a constraint. We just try to minimize the boundary function in the whole space. That's why we require a very small beta. A very large beta. If beta is small, then have divergence. But for the PCAL, basically, theoretically, it's actually we're doing our constraint boundary minimization, the constraint region, the M is oblique manifold. So now give a very good explanation for our PCAL. But our PanCF, because we have simple ball, which is much cheaper projection, so it's better than use the oblique manifold. So that now we can look at our two old methods as a special case of a new method, then give us a better understanding of our old method. We have done some numerical experiments showing the efficiency of our algorithm. So very quickly, the first problem is the simplified Gaussian total energy minimization, where, as I said, the original Gaussian energy minimization, you have 5 terms. So this is simplified, we only use 3 terms. Then we give to show you how the performance of our algorithm. And the second problem is minimize the quadratic function over Stiefel manifold. So basically, a quadratic function minimize and subtracting. And this is a general quadratic function. We just generalize the quadratic term and the first order term by the generalized coefficient by Gaussian distribution. And also the step size, we use the BB step size. We have BB1 and BB2, and actually we're using the alternating BB strategy given by Dye and Fletcher, where is alternating by BB1 and BB2 in turn. We're also doing a post-process. So that means when we finish our algorithm, we're doing one orthogonalization. So that means if our final point, which is have single value decomposition, which is xk, which we just put all the diagonal elements into one, then we get the post process. And by doing this, first of all, we show you theoretical results. If the boundary parameter is large enough, this post process, of course, the post process will be drawing the point from infeasible to feasible. But we can also show you by doing this processing, the new point not only improve the feasibility, but also improve the quality of the point by reducing the boundary function. So that is the result we're showing. So the experiment we have done is the problem generalized is by you can download from a website of Yang Chao And also we test a lot of algorithm compared with the famous SCF, and also a lot of algorithm, particularly we compare with the MOPTQR, which is a package by the group of Professor Abisel, and also OPTM, which is by Zai Wenwen and also Wu Taoying. They also use the BB step side, and also our old method as well. So this is the numerical results. You just look at the final, the last column, which is given the CPU time, which is the one who have the least time, I will mark in red. So you can see for most of the problem, our algorithm will be given the best performance, even though some of them the other method win. For example, the first one, Alanin, which is actually the OPTM, which is the algorithm by Zai Wenwen and Wu Taoying, which is 18.23 second, which is the least time. And our is 1892, slightly worse. And also we can show many of other example. We can show for most of the atom, our algorithm its performs the best. So we also extended our idea to second order method as well. For extending this to second order method, we have to computing the second order gradient, the Hessian matrices of the Party function. As I said, the first order, the gradient of the Party function is already involve the second order derivative for the objective function. So to compute the second order Hessian matrix of the Party function is really intractable, because that will be involving third order derivative of the objective function. So what we could do? So we write down the second order matrices of the Party function into detail. We found those we don't want to compute the difficult term. We found it will be getting very, very small if it's close to the Stiefel manifold. So that means when the term we write in the green, which is the difficult term, then we can throw this term away, because if this term will be getting very small if the point is close to the Stiefel manifold. So then we get a kind of approximation to the second order derivative of Party function. Now added into the red term, I call it WX. So WX is actually is approximation to the second order of matrices of the original Party function. So by doing this, we can get a second order method, because we have approximation of the second order term. Then we can construct a trust region model where you have minimized the quadratic function subject to trust region ball. Because doing a minimize the quadratic function in a ball, which is the standard trust region subproblem, which is easy, which can be shown to easy to get to compute the global minimize in the trust region ball. And even though this is the second order model, but as I said, the second order term is easy to compute. In that way, we can get a second order method for the Party model based on this compact convex constraint. So the algorithm is very simple. So each iteration, you just compute a search direction by solving the trust region subproblem. Then you're moving along this trust region step along this direction. And if 8 in the ball, then we stopping condition satisfied, then we return. Otherwise, we keep doing this secondary iteration. We also can able to prove the convergence result, even though we are not using exact secondary derivative, but the term we threw away is higher order. It's small, getting small. That means we can still prove a quadratic conversion rate of our algorithm. So that is a good, very powerful theoretical result. We prove second-order conversion. Now we do some numerical results for our second-order problem. First of all, we're doing a quotient total energy minimization. We particularly, because using one term is quadratic, because the second term, but we need a nonlinear term, so we're using a nonlinear term here, which is the density, as I said, the density itself is the quadratic term. So the low itself is the quadratic, then this is the quadratic depends on low, then will be the first order term. So this is the problem. The numerical experiment to compare it with the adaptive regular Newton method, which is by Ya-xiang Yuan and his student Hu, and also we also compare with the famous Riemann cross region method by Abisser's group, which is called RTR, which can be downloaded from the website, and also our method. We're choosing the beta, initial beta, as the f-norm of the gradient of the party function. So that is the numerical result compare of these three methods. So for the method, we found our method, not all, I mean, we have tried 5 different cases, and we found 4 of them our method is the fastest method. But for one of them, I think Ya-xiang Yuan's method is slightly fast than for the second example here. So we notice our method is really perform reasonably good. And this is the last 5 set of results. And also similar, I mean, Ya-xiang Yuan's method when one of them as well. I think for the non-smooth case, I will very quickly go to the non-smooth object case because the idea is very similar. So I will not go into detail because for general non-smooth, I have to admit our approach has not yet worked quite well. We don't know how to extend into general non-smooth object function because our approach works very good because we use the closed form Lagrange multiplier. Of course, the symmetric form, that is the transfer, the inner product of x and the grad of the function. So this is because we take the advantage of the orthogonality constraint, use this very special constraint. That is the way we get use a good structure. But for general non-smooth case, we don't know how to get the Lagrange multiplier. So that is we're studying a very simple non-smooth problem. That is we're using the non-smooth term, which is Rx. R is the sum of the 2 norm of each norm of the matrices. So that is called the 2-1 norm. So the 2 norm of each norm, and you sum them up with, a weighted 1 norm. So this is a very special non-smooth function. So I will be using very simple to give you our idea. For this very simple problem, we're able to getting the Lagrange multiplier have a closed form. The reason is because this very special non-smooth function, even though this is a non-smooth function, the Lagrangian multiplier is not, it have very special structure because noticing, because the Punnett function won't have a term of only the Lagrangian multiplier. The Lagrangian multiplier have to appear the Lagrangian multiplier times the matrix X. So that means as long as the X times Lagrangian multiplier is closed, it has a closed form and is continuous, then it's enough. So that is, in the smooth case, I will go very simple. For the smooth case, the Lagrangian multiplier, which is have very closed form. But for the L21 norm regularized case, we can write down the Lagrangian multiplier in a subgradient formula, which looks originally say, oh, this may be not smooth. But in the end, we found the Lagrangian multiplier will be of the gradient of this non-smooth term and time, the non-smooth term times of d of x itself. So that means we found we're using the inner product of x times of d. And the good thing is, even though R itself is non-smooth, but the subgradient of R, the inner product between the subgradient of R and the d will be a smooth function. So that is nicely. So that is we get the closed form of the Lagrangian multiplier. So once we have get this red formula, all the rest is very similar. So that means all the things we do for the smooth case can be extended to the non-smooth case. So I think I will skip the rest of my talk. I just give the idea, I claim. I mean, for those who are interested, you can read our papers. I mean, this is a very simple trick. Even though, I mean, for this non-smooth Rx, then because the Lagrangian multiplier is depends of the inner product of X and the subgradient of R, then we get this inner product smooth. Think about the, I mean, what I say, think about the, you think about the 2-1 norm, you think of the 1 norm, the absolute of X, then the gradient of X will be X divided by the absolute of X. But you times X, then you get X squared divided by the absolute of X. Then you get the absolute of X. So that means it's a continuous function. Then everything, the rest of the part of this part is very similar to the smooth case because I was able to get the Lagrangian multiplier in a closed form and it is smooth, and then we can do the theoretical result. It is smooth, but no, it is continuous but not smooth because it's like a normal function, so it is continuous. The Lagrangian function multiplier is continuous but not smooth. So I mean the rest is very similar, but when you do the same way in a bounded set to minimize the Punnett function. And we can also get the theoretical results very more or less in a similar structure, even though now, because the Lagrangian multiplier is not smooth, it's only continuous, but then the result is weak, for example, but still we can get a very similar convergent result about the equivalent about the first order stationary point and also the stationary point of the original problem, and also the similar result. I think I will go very quickly. I just claim all we have done for the smooth case can be extended to this very special non-smooth case. Then we can get an approximate gradient method for solving this problem. And we have done some numerical results as well. I mean, the global convergence is slightly weak than the smooth case, but we'll be able to prove global convergence result. And also we have compared our method with the MAN-PG, and we're also showing our algorithm have required less computation time per each iteration. And we also done some numerical results with our non-smooth case. And that is, I think, due to the time, I will not keep in, because myself is also midnight in China. So we compare our algorithm with quite a few methods, for example, SOC, and also Parmel, and also MAN-PG, and also 2 versions of the MAN-PG, and also 2 versions of our approach as well. So you can see the CPU time, there's a 2 comparison. One is the iteration number and the CPU time, and our method is really required because we don't require doing orthogonalization per each iteration by minimize only minimize the party function, which each iteration have less computation time. Then the CPU time is much less and have high scalability. So I go to the last slide of my talk. So first of all, I want to say we realize for the very simple Stiefel Manifold constraint, where you minimizing non-linear functions, smooth function subject orthogonality constraint. This, due to the very special structure, we can take the advantage of we have the closed form expression of the Lagrange multiplier. So instead of using ADM technique to update the Lagrange multiplier, we use a closed form of the Lagrange multiplier do have, and this will have end up exact parity function model. And using this exact parity function model, we're noticing this exact parity function, even though it's exact parity function, but can be unbounded in the whole space. Then we do need to have constraint. For example, using a ball. Then we have suggested first order. Sorry, we have a type here, not a fifth. It should be a first order approach, and we have 2 first order approach and also second order approach. We can also use a trust region to get the step size, and also we can extend this idea to some special non-smooth problem. For example, the 2-1 regularized the norm case. As I said, even though we didn't study general non-smooth, but we're thinking about to extending from the 2-1 norm case to more general non-smooth, as long we can obtain the Lagrange multiplier in closed form. So there are more general non-smooth case where we can also get this closed form of the Lagrange multiplier. As long as we can do this for those special non-smooth, more general non-smooth case, we can also use our idea. So I think I hope to show you, to give you the idea using the closed form Lagrange multiplier to help. Use the parity function method can really save computation because you don't, orthogonalization free. That means you don't do any orthogonalization. So from the feasibility point of view, you don't want to keep your point in the feasible set, even though, but by minimizing parity function, it will be automatically close to the feasible set. It won't go away from the feasible set too far away. So think about you're chasing, you have a feasible set, you're really chasing the feasible set, but not really on the surface. So that really, you save your computation. So it's kind of like an inaccuracy approach, but the computation cost per iteration is very small. So that will be the algorithm will be computation very fast. So thank you very much for your attention. Professor Bott?
Thank you very much for the nice talk. Thank you very much. So you already have 2 questions in the chat. So let us start with Rivorkovich. Would you please ask your question?
Yes. As I mentioned in the chat, so you're working on the Stiefel manifold, X transpose X is equal to the identity. So your original problem and also problem 3, these problems can have duality gaps. And you're working with duality, especially when you use the penalty function. However, if you add the redundant constraint, XX transpose is the identity, then theoretically you can prove, and I guess you know this because we have a paper together, that you can close this gap. So if you add this redundant constraint and just do all your work with the penalty function with this extra term, do you think you will get stronger results?
Yeah, I think it should be have a theoretical problem, but the way what we shows if you have minimized the originally penalty function. So in our case, is we trying to minimize the originally penalty function, and we prove if you can get the minimizing, then it will be on the board. That means in this case, we are showing for this case it will be on the let me say if for our case we minimize the penalty function, well, I can only show you it will be near the manifold. So that means it will be end of a first order stationary point. Yeah, you're right. I can only prove the solution will be first order stationary point. Yeah.
But Henry,
I don't know what how you can say. So theoretical, if you the penalty function is the first order point, then you can also have the first order station point. But you have the global minimize of the penalty function, it will be also global minimize in the Stiefel manifold, because the Stiefel manifold is a bounded set. So you are thinking about where minimize a convex set of a non-convex HX, but you're using first order method. So the first order method will be stuck to a local minimize. So there might be possibility you can get a local minimize of the penalty function. But the theoretical result is you get the global minimize of the H, the non-convex function. The global minimize of the non-convex function H, of course, will be the solution of the global minimize of the original problem. So that means the logical is, I mean, you're solving this penalty function. If you get the global minimize, then you get the global minimize of the original problem. But if you get the local minimize of the penalty function, you get the local minimize or original problem. So I don't know whether this is what you're worried about. Henry, sorry.
Not that I'm worried. I just think it would help because it would give you a stronger dual, and you're working on the dual. So,
yeah. I mean, that's. I
think Mark's talk as well. Hidden convexity.
But Henry,
idea.
Henry, I don't understand.
Mark, yeah.
Yeah, are you talking about? But Ya-xiang is talking about a general function f. I mean, for a general function, you cannot close the gap.
No, you can't close the gap, but to the problems you could. But even if you can't close the gap, it's sort of an indicative that you should have a stronger dual by adding redundant constraint.
For a general f, I don't understand what you're saying. I don't think it's true. It may be true for a quadratic, yes, but not for a
no, but well, many of the problems were quadratic.
Not
the
really.
Applications were quadratic.
Well, anyway. So
I think, Mark, I think Henry is saying if working the dual, they may have some of the problem, maybe, as you said, particularly quadratic or particularly special non-smooth.
yeah, for special classes, yeah, sure.
It may have.
More,
but I think for
mostly quadratic ones.
For some problem, I mean, the dual is not easy to obtain, I think, Henry. So because the idea for myself is I'm working the prime problem is to get a very simple algorithm. So that is why I didn't think about the dual. I just want to using the gradient of f, direct very quickly computing. Particularly the original structure of the problem have some sparsity. So that is why I didn't use the dual. But for some, I agree with you. Maybe for some special structure problem, the dual may help. I agree with you. But for my case, that I didn't think about the dual. It's due to think about most of my problem is not the case. I think the dual will not help. I don't know whether I explained clearly.
We have an agreement. So we have a further question by Yu Hong Dai. Would you please ask?
Okay.
So Yu Hong Dai.
Yu Hong, are you there?
Yeah.
Yes. Thank you, Professor Yuan, for your nice talk. I really enjoyed it. So on page 20, you try to omit the red part to get the direction. So I was wondering whether you could you can try to make use of the first part or even have some approximation to the second part of the red part to make a good direction.
Yeah, that is a very good question and comment. I think Yu Hong's idea is because when I saying I using the gradient of the boundary function, then I omit the term where the red term because which is getting very small when it is close to the Stiefel manifold, so I ignore. But Yu Hong saying in the red term, they have two terms. The first term is simple because only the gradient. Maybe I can keep this term. This is a good suggestion. Maybe I can try two versions. One is use this first term to compare whether it's whether will be get a better direction.
Okay.
Yes, maybe we can try. Yeah.
We have a comment by
Okay.
Hong Zhang.
Hi, Professor Yuan. This is Hong Chao. So sorry for my camera. So the computer does not work well. Yeah, thanks for the talk. So, I have a question related to Professor Dai's question. So if we use the gradient and delete the last part, so then this gradient will be accurate when it is close to the feasible set, right?
Yeah.
Yeah. So, but at the beginning, when it is far away from the set, if we use exact gradient, how does it drive the iterates to be close to the set? Can you give us some intuition on this? So it's very interesting. It's a very interesting property. So I want to know some intuitions. You don't need to give us details. So.
Thank you very much for the question. Have you finished? Yeah.
Yes, that's my question. Yeah.
Thanks very much. The problem, I mean, normally for general constraint optimization problem, infeasible method is not easy to get the feasible starting point. So that means for general nonlinear optimization, if you have a constraint, then we have to worry about if you are far away from the feasible set. But for this particularly Stiefel manifold, because it's a very simple constraint. And we can always study from a point which is near to the, actually, I mean, for most of the study, for example, for our case, we can always study from the manifold itself. The idea is we using an infeasible approach is we actually, the method will be always iteration will be very close to the manifold. We're not, the iteration will be not far away from the manifold. That is the idea. This is very different from other infeasible point method. Because, because this is a very special constraint. Then we can already always, the iteration will be traced back, even though not feasible, but it will be not go away from the feasible set far away. So that is the idea.
I wonder, is it particularly the beta, is it large enough? So in the theorem said when beta is large enough, then you can keep it near the feasible set. Is it because of that? The beta, does the beta play the good role there?
Yeah, this is actually, this is a very good question. I think that is really very technical question. Theoretically speaking, you require beta is very large. I mean, for theoretical analysis, but for computationally, we noticed we don't need to take beta too large.
Okay,
because
that's very
beta
interesting.
too large will be actually the method will be not efficient. So that means for real computation, we don't need to take beta too large. Good question, good comment. Yeah.
Okay, thank you.
Thank you. Then I propose to stop here. Thank you very much, Professor Yuan, for the nice talk.
Thank you very much.
For the nice discussion. So we will post the video and the slides on our website. And I want to use this opportunity to thank not only Professor Yuan, but all the speakers of the seminar this year. So we had 30 speakers, 30 great talks. I want to wish you nice holidays, a happy new year. And hopefully we will meet next year in January. So the first speaker of the third season will be Diatush. So I wish you all the best. Thank you for contributing to our seminar. Thank you very much.
Thank you, Adu, for preparing, for doing all the work.
As I do, thanks, Ya-xiang. Okay.
So, Happy New Year.
Mark, see you.
See you.